let's go over the solutions to practice exam number 3. Practice exam number 3. Let argument region in the first quadrant enclosed by the graphs of y equals e to the power of x squared, that quantity minus 1, and y equals 4x. We also want to find the area. And so the graph of this looks like this. And we're looking to find the area that's between the two curves right here. And so actually, let me get rid of that, because if you go through the notes, I always tell you to draw in a representative slice, which looks like this, and there's delta x. And to find the area here, we need to find the points of intersection. This one's obvious, this one's at 0, and then you use your calculator to be able to find that point. I'll go find that in just a minute. So it's going to be the integral from 0 to whatever that point is, and then in the integrand, it's the top function, down at the top, which is the line, 4x, minus the bottom function, and make sure you use parentheses here, all with respect to x. And again, we're just going to find that upper coordinate there. Now, in Desmos, it's easy, but you're supposed to be using your calculator. We showed you how to do this. 1.366. And then you're just going to run this through your calculator and come up with your answer. So, again, in Desmos, this is easy from 0 to 366. Then we got our 4x minus the 1 to the power of x squared minus 1 over to x 2.0873 2.087. It's not a hard setup. Top minus bottom. Now for part B, this is to find the volume of the solid generated when R is revolved around the x-axis. So if we go back here, the x-axis is right here, so we're revolving around the x-axis. There's a gap between the rectangle and the axis of revolution. So that means we're going to use the washer method, the circle cut out. We have our outer radius, which is the further edge. The distance that further edge is to the axis of revolution, which is just top function 4x minus 0, so this is 4x. The inner radius, which is this bit right here, just going to erase that small, that's just our e to the x squared minus 1. So our volume for the washer method, pi, because we're revolving, limits of integration 0 to 1.366. Outer radius, which is that's further away, squared, minus the inner radius squared, all with respect to x. And we get whatever that comes out to be. It's about 28 to change. It did say find the volume, so we actually have to calculate this. We can't just write the integral down and stop, although in B we get to do, or C rather, we get to do that, but not in this one. X squared minus e to x squared minus 1. Make sure you enter all the stuff in correctly. Like this. Oh, I forgot pi. Like, that's awfully small. It's going to put pi out in front here. That's fine. There you go. 20.031. Make sure you round it or truncate. Now for part C, our region R forms the base of the solid whose cross sections perpendicular to the y-axis are squares. Right? Not the expression of all the intervals that means the volume of that solid. So for this one here, we're going to change our picture. And so I got to get rid of all of this stuff. And I'm going to draw my rectangles where the long side is horizontal, and I'm going to do this with respect to y, which means I need to solve each of these equations for y. So y equals 4x, when x is going to be 1/4 y, when I divide both sides by 4. Y equals e to the x squared minus 1, that means y plus 1 is e to the x squared, which means the natural log of y plus 1 is equal to x squared, solving for x. And so x is going to be equal to the square root of the natural log of y plus 1. Now it's the positive root. When we take the square root, it can be a plus or a minus. but I only want positive in the first quadrant. And then this side length right here, this length is the side length of the square. And so I'm on right minus left, so I want this one minus this one for the area of the cross section. Let's see right here. So the area of the cross section is going to be the right function minus the left function. And then it's a square, so we're going to square that length. And then the volume is going to be the integral. Now, I'm going to change the upper limit of integration because now I'm doing this with respect to y. Even though it intersects at the origin, so the y coordinate at the start is 0. But now I need the y coordinate at that point, so which I can go back and get by plugging in 1.366 into one of the functions I'm looking at the graph for the section. So we'll find that in a minute. There is no factor of pi here. There are no circles involved. So don't get a bad habit of just putting pi in front of all these volume questions, because that would not be true. 5.465. And that's it, because it says do not evaluate. So the integrand is correct, the integration is correct, everything looks good. Alright, for 2, we're given that a particle moves on the y-axis with the velocity function v of t is equal to t sine t squared, t is greater than or equal to 0. Don't ignore that part. It says in which direction, up or down, is the particle moving, and t equals 1.5, and y. The velocity does give us the direction of motion, so we got to figure out what v of 1.5 is, and you can just type this into your calculator and see what you get. Actually, this actually comes out to be a positive number. So since the velocity is positive, since v is greater than 0 at t equals 1.5, the object is moving up. Something like that. For letter B, find the acceleration of the particle at t equals 1.5 is the velocity of the particle increasing at t of 1.5, y or y not. So B, the acceleration is going to be, we're going to do the product rule. You can actually do this on your calculator because they showed you how to take the derivative at a point. In case you forgot, you're going to actually do this the longer way. T squared times 2t. And you're going to plug in 1.5. I didn't actually calculate this. T sine t squared. Yeah, I can just put v prime of t in Desmos. Actually, v prime of 1.5. Negative 2.0487. Negative 2.0487. That's the first part. Now, they didn't ask is the object speeding up or slowing down. They wonder if the velocity is increasing or decreasing. That's a different question. A lot of you mixed up speed and velocity here. Speed requires knowing if the velocity and acceleration have the same sign or have different signs. Here, just ask, is the velocity increasing or decreasing? I just need to know if its derivative is positive or negative. And since v prime of 1.5 is less than 0, as I just showed, the velocity is decreasing. I'm going to go look at the question really quickly because I think it asks, is it increasing, decreasing, and not increasing? I guess that's a little redundant. It should be enough. T equals 1.5. Okay, but why do you got that wrong? Because you were thinking speed and they're asking you about velocity. Given the y of t, given y of t is the position function of the particle at t, y is equal to 3, find y of 2. We use a fundamental theorem for this. If I take the integral from 0, I gotta go back and look at the numbers, 0 and 2 of this velocity function, That's going to be y of 2 minus y of 0 by the fundamental theorem. Now this side over here on the left, I can do this on the calculator. Y of 2 is what I'm looking for. Y of 0 is 3, so I'll put 3 in there. Go back to Desmos really quickly and take the integral 0 to t. T will be 0.8268. 8268. So y of 2 will be 3.8268. But you can round this into 7, round off at 826, either way. That's the easiest way to do it, because you get a calculator active on this. You could find the antiderivative and go find C and do a bunch of work, but this is the fastest way. So I'm going to stop there. D, find the total distance traveled by the particle between 0 and 2. I gave you a total distance integral, and it's the integral of the absolute value of the velocity function. All you have to do is plug that into the calculator and then hit the answer. So if you don't know where the absolute value button is on the calculator, you want to find it. And 1.173 out. Should be an easy question. Next time it'll be an easy question. Alright, so for 3, we have this picture for g prime, graphic function g prime, the derivative of function g. On this closed interval, negative 6 to 5 consists of 3 line segments as shown in the figure above, and it is known that g of negative 6 is negative 1. Find the x-coordinate of each critical point on g between the open interval negative 6 and 5. So we've got to figure out where g prime is equal to 0 or g prime is undefined. G prime is not undefined on this interval. There's no holes and no asymptotes. They're trying to confuse you because there's some sharp turns here, which means the derivative of g prime or g double prime isn't going to exist at these sharp turns, but g prime itself does exist at those values. G prime only equals 0 once in the open interval negative 6, 5. Luckily, they didn't penalize me when you also put negative 6 down. Negative 6 is not part of the open interval, so you shouldn't include it. And so the only answer to this one is at x equals 0. That's for part A. For part B, classify each of the points at A, and there's only one, is either relative min, relative max, or neither. And so what's happening to g prime around 0? G prime is positive before and negative after, so that means there's a relative maximum at x equals 0. At x equals 0, there is a relative max because g prime changes from positive to negative at x equals 0. Let's see. By the absolute minimum value of g on the interval from negative 6 to 5. There's only one critical number, okay? And at the critical number, you have a max, a relative max. So the relative or the absolute minimum can only occur at the endpoints, okay? One of the endpoints. Now the graph increases from negative 6. G increases from negative 6 to 0 because g prime is positive, and then G decreases from 0 to 5 because g prime is negative. And so the only place has to be at one of the endpoints. Now the amount of increase is this area under the curve, and you can see there's more area under the curve from negative 6 to 0 than from 0 to 5, and so the graph increases more negative 6 to 0 than it decreases from 0 to 5, and so the minimum is going to be at g of negative 6. But you don't have to do it that way. There's another way. You can just test using the closed interval method. You could do g of negative 6. You could do g g of 6 is negative 1. They told us that. I'm sorry. You can do g of 0, and then you can do g of 5. I'm sorry. I got a little brain fog here. Okay. So we know g of negative 6, so we can move the integral from. Actually, let me do a little side work here because I think this might be a little bit better explanation. Since I know what the integral from negative 6 to 0 g prime of x, this is going to be g of 0 minus g of negative 6. So g of 0 is going to be g of negative 6 plus the integral from negative 6 to 0 of g of prime of x, which is just calculating area under the curve. So this is negative 1 plus. And from negative 6 to 0, we have a triangle, base of 6 and a height of 4. 1 half 6 times 4. That's 24, 12. So this is going to be 11. And for g of 5, this is going to be very similar. This will be g of negative 6 plus the integral from negative 6 to 5, g prime. Now from negative 6 to 0, that's going to be that 11 minus the area that's below from 0 to 5, which is half of 5 times 1, which if you work that out is 8.5, and so the minimum is g of negative 6 equals negative 1. Moving on to D, is x equals 2, negative 2, the location of the point of inflection for the graph of G. A lot of you didn't answer this one very well. A lot of you thought that just because G double prime of negative 2 does not exist, that it automatically guarantees a point of inflection. No, we need to see a change in concavity, but since we don't have the graph, since we don't have G double prime, we're just going to look at the graph of G prime and make the connection. So what's happening at negative 2? At negative 2, we see that G prime is increasing before and decreasing after. That's how we characterize a point of inflection at one point. So excuse the pun there. So yes, there is a point of inflection. The x equals negative 2 is a point of inflection because, if you need the reason for this, G prime is increasing before x equals negative 2 and decreasing after. Similar question in E. It's usually not likely that they're going to give you the same type of answer. So that one is, this one's probably not. It turns out not. Is this a point of inflection? Is there one at 0? No, because the graph is decreasing before and decreasing after. So x equals 0 is not a point of inflection because G prime is decreasing before and after x equals 0. All right, we get the limit as x approaches negative 1. G prime of x minus 2, I think. Check for x squared minus 1. Let's do each of these separately because they love to see them on the AP exam. Now, G prime of negative 1, we have the graph of G prime of negative 1 looks like it's 2. So this is going to be G prime of negative 1 minus 2, which is 2 minus 2, which is 0. And then the limit as x approaches negative 1 and x squared minus 1 is also 0. So we're going to apply the Paul's rule. And then we're going to get the limit as x approaches negative 1. We're going to have G double prime of x divided by 2x. In the denominator, we're going to have a negative 2. G double prime of negative 1 is going to be the slope -1. It's going down. A lot of you put a positive slope there for some strange reasons. -2/2, which comes out to be 1. There's a part G. Pause the video if you need. A lot of you made silly mistakes. You didn't do the product rule. Some of you did not do the product rule here. H of x is 3x times g of x. And g of something is -2 is 7. Find the value of h prime of -2, or explain why it does not exist. So we've got to find h prime of x first. So it's going to be 3 times g of x plus 3x times g prime of x. So h prime of -2 is going to be 3 times g of -2 plus 3 times -2 times g prime of -2. So it's going to be 3 times 7, and they told us that g of was 7 minus 6 times 3 times -2 is a -6. G prime of -2, and I don't remember what that is. So that's 4. So that's 21 minus 24, and you get -3. That's it for question number 3. Alright, so the velocity of particle P moving along the x-axis is followed by a differential function v, where t is measured in seconds, so t is measured in meters per second, so the units of t are shown in the table above. Use the data in the table to approximate p prime of 11, using the average rate of change in v of t from 10 to 12. For the computations that lead to your answer, and indicate units of measure. So this is going to be v of 12 minus v of 10 over 12 minus 10, so it's going to be 20 minus 15 over 2, which is going to be 5 halves. And since the numerator is in meters per second and the denominator is in seconds, the answer is 5 halves meters per second or per second squared. Your choice. 1 point for the units. Interpret v prime of 11 in the context of this problem. In this question, the way it was phrased, they did not say to use units, so you didn't have to. Well, it should, it'd be easier, but anyway, v prime of 11 is, this is the derivative of the velocity, so this is the acceleration of the object, or of point P, of P at t equals 11. I'm going to put seconds down there. So and it should be in meters per second squared. I mean, usually they'll ask you for units, so I'm just putting them in there. If you didn't put it this time, you weren't penalized. But it didn't say to put it. But you're going to have to get 11, and you have to have acceleration or the rate of change of the velocity. Neither one of those are the rules. Rate of change of velocity would be acceptable too. Letter C, justify why there must be time c between 4 and 10 when the velocity is going to be 8. They told us up here that the differentiable function. Okay, so since v is differentiable, v is continuous. Is it 0, 12? 0, 12. Yeah, 0, 12. Okay. Also, I'm sorry, go back to the problem. We're looking from 4 to 10. V of 4 is 6, V of 10 is 15. Okay? V of 4, which is 6, is less than 8, which is less than V of 10, which is 15. Therefore, by intermediate value theorem, there is a C in the open interval from 4 to 10, because that's the interval we're looking at, such that V of C is equal to 8. Yes. D, these right Riemann subs with sum, 3 subintervals, and give it that in the table to approximate the interval from 0 to 12 of v of t. Go from 0 to 12 of v of t. Remember now is which Riemann sum we're supposed to be using. Right, Riemann sum. So if we go to the table, the first interval is from 0 to 4. So from 0 to 4, so 4 minus 0 if you want to show some work. The right endpoint is 6. The next interval is from 4 to 10, and the right interval is from 15. The last one goes from 10 to 12, and the right is 20. 12 minus 10 times 20, and you can stop there. You don't even have to work it out, but this is 24, that's 6 times 15 is 90, plus 40, which is 154. Letter E. This was the substitution problem they put on here. This is how they're going to put substitution on the free response question if it's there. Not all the time, but this is common. So you should work this out. Okay, so we're going to let u equal t over 2 minus 2. So du is going to be 1/2 dt. I don't have that half, so I'm going to multiply both sides by 2 to balance out the half and get just a dt over here. So I'm going to use that 2 and then du over here. I have v prime of u right here. Now I'm going to change my limits of integration. If you watch the video for this, I'm going to put 4 in for t here. 4 divided by 2 is 2 minus 2 is 0. And I'm going to plug the 12 in over here. 12 divided by 2 is 6. 6 minus 2 is 4. Now I can forget about the variable t. 2 times, that's our derivative of v prime is going to be v, so v of u. 0 and 4 are u values, so this is going to be 2 times v of 4 minus v of 0. V of 4, I don't remember. What was that? V of 4 was 6, v of 0 was 2. So this is 6 minus 2, which is 4 times 2 is 8. Alright, letter F. Pause the video whenever you need to. Rewind it. We have letter F. Let h of x be equal to the integral 2 to 4x b of 3t dt, and we want to find h prime of 1. So we got to find h prime of x first. A lot of you messed up the fundamental theorem here. We're getting better at it, but still got some work to do. There's a chain rule since we have 4x here. But I got to plug in the 4x from t and then multiply by the derivative of 4x, which is just 4. So this is going to be 4 times v of 12x, and so h prime of, it's got to be 1, right? So h prime of 1 is going to be 4 times v of 12, and v of 12 was 20. So this will be 4 times 20, which is just 80. So 80. G. Position of the second particle cubed and multiplied by twice the function g. It is known that g of 4 is 7. G prime of 4 is negative 3. G double prime of 4 is negative 2. Is the speed of the particle increasing or decreasing? Well, we give you all the stuff here. We need to know about these two. Do they have the same sign or different signs? And since the signs are the same, the object is speeding up. Since g prime and g double prime have the same sign, the q is speeding up. Excuse my screw. Letter H. Let y fix a particular solution to this differential equation. dy squared dx to x, 3x squared minus y cubed. F of 2 is equal to 1. Right equation for line tangent to a graph of f of 2, 1. The reason for tangent line, I need the slope at 2, 1. So he's got to plug 2 in for x, so 3 times 2 squared, and 1 in for y. So that's going to be 12. Nope. Oops, yeah, there is 12, but it's 12 minus 1, so that's 11. And so the equation of tangent line is going to be y equals 11 times x minus 2 plus 1. Copy that down there. That is the answer here. Yeah, that's it. Alright, ladies and gentlemen, go study. Learn from your mistakes.